So now let us look at the scenario. So what I have is x1, x2, xn has a known distribution function f theta. Theta belongs to theta. So it says, given true state of nature to be theta, x1, x2, xn have a probability distribution of f of x given theta, but here theta is considered to be a random variable. So it is, in certain sense, is a conditional distribution of x1, x2, xn, given that the random variable s is realized as theta. So this can be treated as conditional distribution of sample s, sample x, given then the state of nature, which is random, is realized as theta. Right? As you vary theta, you get a different conditional distribution. And why this is happening? Because I'm now considering theta to be a random variable. And in the frequentist approach, this was distribution of x1, x2, xn given theta, when theta is the true state of nature. So in the Bayesian setup, this can be treated as conditional distribution of x given s is equal to theta. I'll try to look at f theta or f s theta to be PDF of s. So which is a prior distribution. As I said, sometimes prior distribution may be available. So I have a prior distribution, prior knowledge about the unknown state of nature. So unknown state of nature is considered as a realization of this random variable s, which has a PDF fs theta. So this is a prior distribution. So let's look at what are the sources of information about the true state of nature. In the frequentist approach, I had only one source of information about unknown state of nature, which was the sample, x1, x2, xn. But now, I have a prior information. That means from the beginning, I had some information about theta, true unknown state of nature. By taking the sample, you have got some more information about the unknown state of nature. So what I do is, this prior information, to begin with, I have a prior information. Then second stage, I have a data. So let me write down the flow. So what are the sources of information about unknown state of nature? So one is the prior fs theta, and then a data, this has PDF. Let me call this as f theta. Data. Basically, this is a distribution of, this is a PDF of x given s is equal to theta. So what I do is, after I have taken a data, I would like to update my prior information. So what I do is, I combine this and I update my prior information. To begin with, I had a prior information. After I have taken a data, I have additional information about unknown state of nature, so I update it. So that means I'm talking about information about theta when I have observed now x. This was the information about theta without observing anything. Now I observed x, so I would like to update my prior information. So I'm talking about the information about theta when I have a given data. So in a sense, I'm talking about the distribution of a known state of nature, which is S, given x. So which is called the posterior distribution. Which is nothing but distribution of S, which has been updated, which is an updation of prior distribution fs theta given x equal to x. So let us see. So posterior distribution is nothing but distribution of S given x equal to x, which is same as. So what I do is I look at q theta given x, which is posterior PDF of S given that you have observed data as small x. So you know that conditional distribution is same as joint upon marginal. Joint of q theta comma x, so that means joint of S and x. Joint of S and x, so let me write down this as joint of S and x, S at the point theta, x at the point small theta, divided by marginal of x at x. Let me just add a word of caution. In the Bayesian framework, this is not a marginal of x, because here I am considering theta to be a random variable. So this f theta, which in the frequentist approach we call this as a marginal of x, but in the Bayesian framework, I don't call it a marginal of x. It is in fact a conditional distribution of x given s is equal to theta. That means given that the true state of nature, which is random, is given to be a fixed quantity theta. So it is a conditional distribution. And that is why this fxx is not same as f theta x. Okay? Now this is same as f of conditional, joint is same as conditional, f of s given x, theta given x. Sorry, I should put it the other way. F of x given s, x given theta, into f s theta, which was my prior distribution, divided by actually this fxx, I can get from the numerator, because numerator gives me a joint, so I can get the marginal of x by just integrating it out, unwanted variable theta. So this is same as f of x given s. Of course, in the discrete case, you can replace these integrals by summation signs. But what is fx s x given theta? This was nothing but, in the frequentist approach, the distribution of x given theta. So this is f theta x, fs theta, which is the prior distribution, divided by integral over theta, f of x given as. So in this case, it makes sense to concentrate only on the posterior distribution or the posterior PDF, because whatever information about theta you have, it is contained in the posterior distribution. So information about the data, information about the unknown state of nature you had from prior distribution, from data, both have been combined, or the prior distribution has been updated to get the posterior distribution. And this is a posterior PDF which contains all the information which you have at your hand about theta. So that means posterior distribution should play an important role in Bayesian analysis. And we'll see that is the case. Before that, let me see if I have to find the Bayes rule, what I should do. So you can write down this posterior distribution contains all the available information about unknown state of nature. And this would be justified. This is what my intuition suggests, that everything, what should matter to me now is only the posterior distribution. And that would justify theoretically as well. So for that, I should try to find, so in the Bayesian setup, it makes sense to minimize the average risk or to find the Bayes rule. And we'll see that Bayes rule is the one which minimizes the posterior risk. So I can talk about posterior risk. The usual risk was the frequentist risk. I can talk about the posterior risk or the posterior loss. So let me write down this as a theorem. So delta, let delta be such that expected value of s given x equal to x. So this is, you can look at expected value of unknown state of nature given data. L theta, theta is represented by a random quantity which is s. So let delta naught x is such that it is infimum over all A belonging to A of expected value of L SA. So this is basically, if you look at, this is again here S given x equal to x. So this is posterior loss. Theta was unknown. So L theta A was the loss when theta is the true state of nature. But theta is unknown, which is the information about theta is contained in the posterior distribution, which is same as distribution of S given x equal to x. So I look at what is the average loss with respect to the posterior distribution. That is what exactly I trying to do. And what it says is the Bayes rule will be the one which minimizes the posterior expected loss. And that way it justifies why posterior distribution is important in Bayesian analysis. And which is what my intuition was suggesting. That all the information about theta is contained in posterior distribution. So it is only the posterior distribution which should matter. And which is justified through this result. Now one thing you know that, here this delta naught, you are minimizing this with respect to A. So if the minimizer exists, it only depends on A, so A would be a function of x. It would only be a function of x. No further randomization is required. So here, this Bayes rule is always non-randomized. There is no randomization because it says you consider delta naught x to be 1, which minimizes this. If I try to minimize this, the minimizing thing at the best is going to depend on what this x is, because s would be averaged out. So the proof is let delta dot given x be any randomized estimator. So let yx be the random variable corresponding to to delta dot x. As you know that as you vary x over the sample space, that means depending on what data you get, your randomization changes. So random variable yx changes because it depends on the data. Because that is what you're saying. After you have obtained a data, you do a randomization to get an estimator. So after you have obtained a data, you observe another random variable yx, and that you consider as a estimator. Okay, so let us try to see. So here, two randomizations are there. One is a randomization which is done by yx. After you have taken it observer data, you do a randomization yx, and then x itself is a random. So here when we talk about the risk function, average are involved at two stages. So first average is L star theta delta x. And what is that? That is nothing but expected value of L theta for the time being. A is a random quantity which is yx. All right. So I can talk about R delta theta. R delta theta is now I am taking average distributive distribution of x given theta. But now theta here is a random variable. So it is not a distribution of x given theta, it is a distribution of conditional distribution of x given s is equal to theta. So this is same as expected value of x given s is equal to theta of L star theta delta x. So two randomizations. One randomization over here. This expectation is with respect to random variable yx for a given x fixed. Yeah. Now I vary x and I take the various average with respect to x with respect to conditional distribution of x given s equal to theta. Now this is nothing but expected value of x given s equal to theta of L star theta. L star I can put the value from there. So this is same as expected value of y of x. So that you, this I am putting so that you remember this expectation is with respect to which random variable? L theta yx. Now what I have to do? I have to consider R delta pi. Pi is the given prior distribution to me, because when I talk about a Bayes estimator, it is always in reference to a given prior distribution. So here I assume pi be a given prior distribution. What is this? This is nothing but expected value of, you take the average of R delta theta when theta is considered to be a random variable, or theta is considered as a realization of a random variable s. So it is expected value of s R delta s. R delta s, I can get everything from here. So E of s, E of x, now it becomes s because there is no fix. S is a random variable now. Then expected value of yx of L of theta is a random variable s. So s equal to theta is s equal to s. So s yx. Okay. Now this is the expectation of a conditional expectation. So this can be written as a joint expectation with respect to x and s. So let me not change much for the time being. Let me go step by step. So what I'm trying to do basically is, I'm trying to change the order of integrations, and I am trying to take out the expectation with respect to marginal of x as the outermost expectation. And then the inner expectation I try to minimize for every value of that random variable capital X, which is the data. That is what exactly I'm trying to do. And that is why I converted this two expectations, which were expectation of a conditional expectation, a joint expectation. Now I convert this into, again, expectation of a conditional expectation, except that now I write down this as E of X into E of S given X. So E of X is the marginal of X, which is different from F theta. It is a marginal in reference to the Bayesian setup. Then expected value of S given X, expected value of Yx of L theta Yx. Good. Now note that over here, in both the things here, X is fixed, S given X is fixed, so I can interchange because this expectation does not depend on this expectation. So I can write down this as E of X, E of Yx, and then E of S given X of L theta Yx. Now let's look at only the inside thing. What is given to me? E of S given X equal to X of LSA is minimized by delta naught X. So whatever A you put it over here, it is minimum when you replace A by delta naught X. So here it was Yx, so that means if I here put by delta naught X, I get a minimum, a smaller quantity. And you know that if Y1 is less than or equal to Y2, then expect Y1 is less than or equal to Y2. So whatever X may be, this quantity is always greater than or equal to, because delta naught X minimizes this thing. So L of S given X, L theta delta naught X. Because whatever Yx you can treat as A, whatever A may be or whatever Yx may be, this is always minimized by delta naught X. So what do you get? So this is always greater than or equal to E of X, E of Yx, E of S given X of L theta delta naught X. Now there is no Yx over here, so this expectation will not play any role. There is no Yx. Yx has vanished. Because Yx was over here, I replace it by delta naught X, so that has vanished. So this expectation will not play any role. So this is same as E of X, E of S given X. This expectation of a conditional expectation, so this again I can write down as a joint expectation, E of S and X, which I again can write down as expectation of a conditional expectation. In fact, if you look at, this is nothing but ES of R delta S. So if you want, this can be written as I said, this expectation of a conditional expectation can be written as a joint expectation, E of X and S. Then I can write down that as the expectation of conditional expectation. So that is same as E of S, E of X given S of L theta delta naught X. But what is this quantity? This is your frequentist disk of delta naught. And which is nothing but R delta naught pi. So what you have shown? You took an arbitrary estimator delta, you considered its base risk, and you saw that that is always greater than or equal to the Bayes risk of delta naught. So this means delta naught is Bayes. So as I told in the beginning, a Bayes rule will always, there will always be a Bayes rule which will be non-randomized. So that means for finding Bayes rule, it is enough to consider only non-randomized estimators for finding Bayes estimator, a Bayes estimator. It is enough to consider only non-randomized estimator. Let me give a definition of a Bayes action. So the decision rule or the estimator or decision rule delta naught satisfying, what does it does is minimizes the posterior loss. So that means expected value of S given x equal to x of LS delta naught as infimum over A belonging to A so this is a posterior loss, right? So any delta naught x which minimizes the posterior loss for every x is called Bayes action. So in the last theorem, what you have essentially proved is a Bayes estimator is same as Bayes action. So what it says is you just try to find out the Bayes action. And what is the Bayes action? You try to look at the posterior distribution of theta given x equal to x and see what is the average loss, average taken over theta, which is s, and then try to minimize this quantity. Whatever ax you get for different values of x, that gives you the Bayes estimator. There may be other Bayes estimator also, but there is always a Bayes estimator which is a Bayes action. So this is a very useful technique to find Bayes action. And what Bayes action says is very simple, because you see this is all based on your intuition, because my intuition suggested the moment I had a prior information, my intuition suggested that I should look at the sources of information about theta. One was the prior information. The other was the information contained in x, and which is equivalent to saying that distribution information contained in distribution of x given theta. Says now update prior information based on the information which I have got through the observation, which says that you consider the PDF of theta given that you have observed the data as x, the distribution of theta given x, which we call as a posterior distribution. Then we said that our intuition suggests that all the information about theta is contained in the posterior distribution, so I need not bother about prior distribution now or the frequentist distribution which was f theta x, because all that, whatever was there in these two PDFs, that has been squeezed and gotten into the posterior distribution. If I have to consider posterior distribution, the natural thing to consider is the posterior loss, which is this, and think of minimizing this. So what this result suggests is once we do that, we minimize the posterior loss, that gives me the Bayes estimator, which is the one which minimizes the average risk over all thetas. So let me stop over here. We'll take from this point onwards in the next lecture. So that's all for today. Thank you very much.